Hi, in this third worked example video for Unit 8, we're going to go through some examples involving orthonormal bases. Let's first of all start with an example computing a projection with an orthonormal basis. We want to find the projection of a vector u from R5 onto the subspace of R5 spanned by these four vectors q1, 2, 3, and 4 given here. I recommend that you pause your video, work through this solution on your own, and then resume to compare with my worked solution. So if this was a normal basis, how would we proceed? We would proceed by constructing a matrix whose columns were the vectors of interest, the basis vectors, I should say. And we could then compute the projection of u onto the vector space using the standard result for the projection space, for the projection. And so we are still going to start with that same process, constructing the matrix Q, whose columns are the basis vectors we were given. However, this basis set, this set of basis vectors, is orthonormal. We can see that, first of all, by checking the dot product. The dot product will be the sum of the product of corresponding entries, 0 plus 0 plus 0 plus 0 plus 0. We have a 0. 1 over 2 root 2 minus 1 over 2 root 2 plus 0 plus 0 plus 0. 0 plus 0 plus 0 plus 0 plus 0. I'm not going to go through all of the pairs, but you can verify that in fact the dot product of these vectors is all 0. They also are all normal in that if we sum up the squares of the entries in any column, we get 1. Quarter plus a quarter plus 0 plus a quarter plus a quarter is 1. Half plus a half is 1, and so on. When we have a set of vectors whose a matrix whose columns are both orthogonal to each other and normal, when we compute Q transpose Q, we will get the identity matrix. And if Q transpose Q is the identity matrix, the inverse of the identity is the identity, this piece just disappears and we're left with a simplified projection. So we don't have to go through the more involved process of finding a projection. We use this simplified approach. Okay. As always, we are going to break this product into pairs of products. I recommend starting with this one, Q transpose U, just because U is a vector, and so this product will give us another vector, whereas Q transpose would give us a matrix. It will simplify our work by computing the product in this order. Q transpose U, we simply transpose our vector, multiply it by our target, and then evaluate a half plus 1 plus 0 plus 2 plus 2.5 gives us 6. 0 plus 0 plus 3 plus 0 plus 0 gives us 3. 1 over root 2 minus 2 over root 2 plus 0 plus 0 plus 0 gives us negative 1 over root 2. And 0 plus 0 plus 0 plus 4 over root 2 minus 5 over root 2 also gives us negative 1 over root 2. Now that we have that piece, we're ready to compute the second portion. We simply substitute in the value we just calculated for Q transpose U, and now multiply it with our matrix Q. And again, evaluate the product. Half times 6 is 3, plus 0 minus 1/2, because 1 over root 2 times 1 over root 2 is 1/2, gives us 3 minus 1/2, or 5/2. For our second entry, we get 3 plus 0 plus 1/2, or 7/5. For our third entry, we have 0 plus 3 plus 0 plus 0, 3. For our third entry, again, we have 1/2 plus 0 plus 0, 3 plus 0 plus 0 minus 1/2 gives us 5/2. And for our last entry, 3 plus 0 plus 0 plus 1/2 gives us 7/5. Our final answer is this vector here. The projection of U onto the vector space spanned by this orthonormal set is given here. The process is conceptually similar to finding the projection for a non-orthonormal basis, but the work is greatly simplified because we don't have that inverse of Q transpose Q to worry about. Okay. Projections are easy when we have an orthonormal basis. In the next example, let's go over the process of finding an orthonormal basis from a general basis. Let's find an orthonormal basis for the vector space spanned by a set of linearly independent vectors v1, v2, and v3 given here. Again, I recommend that you pause your video, try to solve this problem on your own, and then resume to follow the worked solution. This sort of process is always solved. We can always find an orthonormal basis using the Gram-Schmidt approach. We break this into two pieces. The first is to generate an orthogonal basis, and then to normalize it, we generate the orthogonal basis using a sequence of substitutions where we first of all assign our first vector to simply be the first vector from the set. We then define a second vector by taking the second vector from the set and subtracting from that the projection of that vector onto our first orthogonal vector. And then a third vector by drawing the third vector from the original set, subtracting off the projection of that vector onto the first orthogonal vector and onto the second orthogonal vector. And this will give us an orthogonal set. Let's go through that process. So our first vector, v1, is just directly assigned to be w1, our first orthogonal vector. We are then going to want to compute our second orthogonal vector by taking our second vector from our original set and subtracting off the projection of that onto w1. This is going to involve a ratio of the dot product of v2 with w1 and the dot product of w1 with itself. So we can start off by computing those two terms. The dot product of w1 with itself is the sum of the squares of its terms. 1 plus 1 plus 1 plus 1 is 4. The dot product of w1 with v2 is the sum of the product of corresponding terms. Since W1 is all ones, this is just going to be the sum of the entries in V2. 2 plus 2 plus 1 plus 1 is 6. Right? So what we need to compute is V2 minus the projection of V2 onto W1. It's in the direction of W1 and scaled by this ratio of 6/4, or 3/2. 2 minus 3/2 is 1/2. 2 minus 3/2 is 1/2. 1 minus 3/2 is negative 1/2. And 1 minus 3/2 is again negative 1/2. We can simply use this as our next vector, and that's a completely fine thing to do. It often simplifies the arithmetic of Gram-Schmidt orthogonalization to have vectors that are in whole numbers, because we're going to need to be computing these dot products and taking ratios of the dot products. When we have fractional values in our individual vectors, this normalization, or this sort of scaling constant, involves fractions over fractions, which can be just error-prone to by-hand calculation. And so I tend to, when I get a result like this, with many fractional entries, simply scale this vector by an appropriate constant to get a vector in the same direction, but with all small integer values. So multiplying this whole vector by 2 transforms it to 1, 1, minus 1, 1. We can do this because all we're trying to do at this point is try to find an orthogonal basis. And if we change the length of a vector, it doesn't change whether it is orthogonal or not. We can also double check here that W2 and W1 are in fact orthogonal by adding up the product of the corresponding entries. 1 plus 1 minus 1 minus 1 gives us 0. Okay, so we now have 2 orthogonal vectors. Our next step is to generate the third. The third is found by taking our third vector, V3, and subtracting off the projection of that, V3, onto both W1 and W2. This is again going to involve ratios of dot products. We've already computed the dot product of W1 with itself, it's 4. We also compute the dot product of W1 with V3, which is 1 plus 2 plus 2 plus 1 is again 6. We compute the dot product of W2 with itself, which is the sum of the squares of the terms, 1 plus 1 plus 1 plus 1 is 4. And the dot product of W2 with V3 is 1 plus 2 minus 2 minus 1 is in fact 0. Seems that V3 and W2 are in fact orthogonal. Once we've computed these individual dot products, we can put together the expression we want to evaluate, V3 from our original set, minus the projection onto W1, so this is going to be W1 from our orthogonal set, minus our scaling factor, multiplied by our scaling factor of 6/4, minus a vector in the direction of W2, here's W2, multiplied by the scaling factor. The fact that the scaling factor has a numerator of 0 here means this term is not going to play a role in the final answer. 1 minus 3/2 times 1 is -1/2. 2 minus 3/2 of 1 minus 0 is plus 1/2. 2 minus 3/2 plus 0 is 1/2. 1 minus 3/2 plus 0 is negative 1/2. Again, we can scale this by multiplying by 2 to give a vector in the same direction, but with all integer values. At this point, we started with 3 linearly independent vectors. We have 3 orthogonal vectors. This set W1, W2, and W3 is an orthogonal basis for the same vector space. Our last step is to normalize these vectors, convert them to vectors in the same direction, but with a length of 1. We do this by taking each of these vectors and scaling them by 1 over their length, 1 over their norm, where this length is given by the square root of the dot product of the vector with itself. Computing these dot products, because all of them have terms of just plus or minus 1, all of them in fact have the same dot product with themselves. 1 plus 1 plus 1 plus 1 is 4. In this case, they all are vectors of the same length, so they're all going to have the same scaling factor. This is not a general result. Q1, we multiply by 1 over the square root of 4, or 1/2, multiplied by W1, gives us a vector of all halves. Q2, scaling by 1 over square root of 4, or 1/2, multiplied by W2, gives us 1/2, 1/2, negative 1/2, negative 1/2. And Q3, multiplied by the scaling factor of 1 over square root of 4, gives us negative 1/2, 1/2, 1/2, negative 1/2. This is now not only an orthogonal basis, it is an orthonormal basis. Our final orthonormal basis, Q1, Q2, and Q3, is given by this set, and these 3 vectors span the same vector space that we started with. All right, we've gone through 2 examples, one showing how we can compute a projection using an orthonormal basis, and where things become much more simplified compared to a general basis. And secondly, an example how we compute an orthonormal basis given an arbitrary basis. You'll have more practice on with these ideas on the homework. That ends our worked examples for Unit 8. Thank you, and goodbye.